1,055. That is how many stocks traded on the New York Stock Exchange in 1965. Today, there are over 6,000 globally listed equities in the United States alone. No analyst can study every single one. So how does a portfolio manager draw conclusions about the entire market by studying just 30 or 50 stocks? The answer is sampling. And the mathematics behind it is so powerful that by studying a tiny fraction of a population, you can make statements about the whole population with 95% or 99% confidence. But only if you sample correctly. Get the sampling method wrong, and your conclusions are worthless. The CFA exam tests exactly this, knowing when your sample tells you truth and when it lies. In this lesson, you will master sampling and estimation for the CFA exam. We start with sampling methods. Simple random sampling, where every member of the population has an equal chance of selection. Stratified random sampling, which divides the population into groups and samples from each. Then sampling distribution and sampling error, the gap between your sample statistic and the true population parameter. The central limit theorem, the single most important theorem in statistics. Standard error of the sample mean. Point estimates and confidence intervals. How to build a range around your estimate with known probability. The t-distribution versus the z-distribution, and when to use each. Properties of a good estimator. And the biases that destroy sample validity. Data snooping, survivorship bias, look-ahead bias, sample selection bias, and time period bias. 5 exam questions with full wrong answer analysis. Sampling and estimation. Lesson 7 of CFA Level 1, Quantitative Methods. Part 1. Sampling Methods. How to draw conclusions about millions from just a handful. Imagine you want to know the average return of all U.S. large-cap stocks over the past decade. There are roughly 500 stocks in the S&P 500. You could study all 500. That is called a census, examining every member of the population. But what if your population is all global equities? Now you have tens of thousands of stocks across dozens of exchanges, different currencies, different reporting standards. A census becomes impractical. So you take a sample. A sample is a subset of the population. The key question is how you select that subset. If your selection method introduces bias, your sample will systematically misrepresent the population. The CFA curriculum covers 2 primary sampling methods: simple random sampling and stratified random sampling. Simple random sampling means every member of the population has an equal probability of being selected. Think of it like putting every stock's ticker symbol into a hat and drawing 50 at random. No stock has a better or worse chance than any other. The beauty of simple random sampling is that it produces an unbiased estimate of the population parameter. On average, your sample mean will equal the true population mean. But here is the limitation. Suppose your population has subgroups that behave very differently. Large cap stocks versus small cap stocks. Growth versus value. US versus international. With simple random sampling, you might accidentally draw a sample that overrepresents one subgroup and underrepresents another. By pure chance, you could draw 45 large caps and only 5 small caps from a population that is evenly split. Your sample mean would then be biased toward large cap behavior. This is where stratified sampling becomes essential. Stratified random sampling fixes this problem. You divide the population into subgroups called strata. Each stratum is a group of members that share a common characteristic: large caps in one stratum, mid caps in another, small caps in a third. Then you take a simple random sample from each stratum. If your population is 40% large cap, 30% mid cap, and 30% small cap, your sample mirrors that same proportion. Why is this better? Because stratification guarantees that every subgroup is represented proportionally. You cannot accidentally get an all large cap sample. The CFA exam loves to test this distinction. Stratified sampling produces more precise estimates than simple random sampling when the strata are internally homogeneous but differ from each other. In plain English, if large caps behave similarly to each other but differently from small caps, stratification dramatically reduces your sampling error. Part 2. Sampling distribution and sampling error. The gap between what your sample says and what is actually true. Here is an idea that trips up many candidates. Suppose the true average return of all US stocks is 10%. You draw a random sample of 30 stocks and calculate their average return. You get 11.2%. Your friend draws a different random sample of 30 stocks. She gets 9.1%. Another analyst draws 30 stocks and gets 10.4%. Each sample gives a different answer. None of them are exactly 10%. The difference between your sample statistic and the true population parameter is called sampling error. Sampling error equals the sample statistic minus the population parameter. This is not a mistake. It is not a flaw in your methodology. It is an inherent consequence of studying a part instead of the whole. Sampling error exists even in a perfectly conducted study with perfect random sampling. The CFA exam tests whether you understand this distinction. Sampling error is not caused by bad sampling, it is caused by sampling itself. Now, here's the powerful idea. If you could draw every possible sample of size 30 from the population and calculate the mean of each sample, you would get thousands and thousands of sample means. The distribution of all those sample means is called the sampling distribution of the sample mean, not the distribution of the data, not the distribution of the population, the distribution of the statistic itself across all possible samples. This is a crucial distinction. The population might follow any shape, skewed, uniform, bimodal, but the sampling distribution of the mean has very specific properties that we can exploit mathematically. The mean of the sampling distribution equals the population mean mu. If you averaged all possible sample means, you would get exactly the true population mean. This is why the sample mean is called an unbiased estimator of the population mean. Part 3. The Central Limit Theorem, the most important theorem in statistics, and the foundation of everything that follows. The Central Limit Theorem says this. Given a population with mean mu and finite variance sigma squared, the sampling distribution of the sample mean approaches a normal distribution as the sample size n becomes large. Read that again carefully. It does not matter what the population looks like. The population could be heavily skewed. It could be uniform. It could be bimodal with two humps. As long as your sample size is large enough, the distribution of sample means will be approximately normal. Why does this matter so much? Because once we know the sampling distribution is normal, we can use everything we learned about the normal distribution. Z-scores, probability tables, confidence intervals. The central limit theorem is what makes statistical inference possible for any population shape. The CFA exam considers a sample size of 30 or more as large enough for the CLT to apply. Below 30, you need additional assumptions about the population distribution. The standard deviation of the sampling distribution has a special name. It is called the standard error of the sample mean. The formula is sigma sub x bar equals sigma divided by the square root of n. Let me break this down. Sigma is the population's standard deviation, how spread out the individual data points are. N is your sample size. And sigma sub x bar is how spread out the sample means are across all possible samples. Notice the square root of n in the denominator. As your sample size increases, the standard error decreases. A sample of 100 has half the standard error of a sample of 25. Because the square root of 100 is 10, and the square root of 25 is 5. 10 divided by 5 is 2. This is the mathematical reason why larger samples give more precise estimates. The sample means cluster more tightly around the true population mean. But there is diminishing returns. Going from n equals 10 to n equals 100 cuts standard error by about 68%. Going from n equals 100 to n equals 1000 only cuts it by another 68%. You need to quadruple your sample size to cut standard error in half. Let me show you with numbers. Suppose the population standard deviation of annual stock returns is 20%. That is sigma equals 0.20. If you take a sample of 25 stocks, the standard error is 20% divided by the square root of 25. The square root of 25 is 5. 20 divided by 5 equals 4%. So the standard error with 25 stocks is 4%. Your sample means will typically be within about 4 percentage points of the true population mean. Now increase to 100 stocks. 20% divided by the square root of 100. Square root of 100 is 10. 20 divided by 10 equals 2%. With 100 stocks, your estimates are twice as precise. Typical deviation from the truth is now only about 2 percentage points. And with 400 stocks, 20 divided by 20 equals 1%. Quadrupling the sample from 100 to 400 cut the standard error in half, from 2% to 1%. This is the diminishing returns. One critical detail: the exam tests. In practice, you almost never know the true population, standard deviation sigma. If you knew sigma, you would already know a lot about the population. So instead, you estimate the standard error using the sample standard deviation S. The estimated standard error is S divided by the square root of n. When you use S instead of sigma, you introduce additional uncertainty. And this additional uncertainty is exactly why we sometimes need the t-distribution instead of the z-distribution. We will get to that distinction shortly. For now, remember two formulas. When sigma is known, standard error equals sigma over root n. When sigma is unknown, standard error is estimated as S over root n. The CFA exam will tell you whether sigma is known or unknown. This determines which distribution you use for confidence intervals. Part 4. Point estimates in confidence intervals. From a single number to a range with known probability. A point estimate is a single number used to estimate a population parameter. The sample mean x bar is a point estimate of the population mean mu. But a point estimate by itself tells you nothing about precision. If I tell you the average return is 10.5%, you should immediately ask, how confident are you? Plus or minus 1%, plus or minus 5%. A confidence interval answers that question. It gives you a range of values within which the true population parameter is likely to fall, along with a specified probability. Think of it this way. A point estimate is like saying the temperature tomorrow will be 72 degrees. A confidence interval is like saying there is a 95% chance the temperature will be between 68 and 76 degrees. The interval is more useful because it communicates both the estimate and the uncertainty. The confidence interval formula is x bar plus or minus the reliability factor times the standard error. Let me explain each piece. X bar is your sample mean, your best estimate of the true population mean. The reliability factor is a number from either the z-table or the t-table, depending on the situation. It determines how wide your interval needs to be for a given confidence level. For 95% confidence using the z-distribution, the reliability factor is 1.96. For 90% confidence, it is 1.645. For 99% confidence, it is 2.575. The standard error is sigma over root n if sigma is known, or S over root n if sigma is unknown. The product of the reliability factor and the standard error gives you the margin of error, the half-width of your confidence interval. Higher confidence means a wider interval. You are more confident precisely because you are casting a wider net. Let me work through a full example. Sample of 64 mutual funds has a mean annual return of 8.6% with a known population standard deviation of 12%. Construct a 95% confidence interval for the true mean return. Step 1. Identify the pieces. X bar equals 8.6%. Sigma equals 12%, and we are told it is known. N equals 64. Step 2. Calculate the standard error. Sigma over root n equals 12, divided by the square root of 64. Square root of 64 is 8. 12 divided by 8 equals 1.5%. Step 3. Find the reliability factor. For 95% confidence with the z-distribution, z equals 1.96. Step 4. Calculate the margin of error. 1.96 times 1.5 equals 2.94%. Step 5. Build the interval. 8.6 minus 2.94 equals 5.66%. 8.6 plus 2.94 equals 11.54%. We are 95% confident that the true mean return of all mutual funds falls between 5.66% and 11.54%. A critical exam trap in confidence interval interpretation. Many candidates say the confidence interval means there is a 95% probability that the true mean is between 5.66 and 11.54%. That sounds right, but technically it is wrong. The true population mean is a fixed number. It is not random. It either falls in this interval or it does not. There is no probability involved for a fixed number. The correct interpretation is this. If we were to draw many samples of 64 funds and construct a 95% confidence interval from each sample, then 95% of those intervals would contain the true population mean. The probability statement is about the procedure, not about the parameter. The CFA exam has tested this exact distinction. If a question asks about the correct interpretation of a confidence interval, look for the answer that describes the repeated sampling interpretation, not the probability of the parameter being in the range. Part 5. The t-distribution. What to use when population variance is unknown, which is almost always. In the real world, you almost never know the true population standard deviation. You estimate it from your sample using S instead of sigma. When you substitute S for sigma, the sampling distribution is no longer exactly normal. It follows a t-distribution instead. The t-distribution looks like a normal distribution, bell-shaped and symmetric around 0. But it has fatter tails. Fatter tails means more probability in the extreme regions. This makes sense intuitively. Since you are estimating the standard deviation, you have extra uncertainty. The fatter tails account for that extra uncertainty by making extreme outcomes more probable. The t-distribution is defined by its degrees of freedom, which equal n-1 for a single sample. As degrees of freedom increase, the t-distribution approaches the normal distribution. At 30 degrees of freedom, the t-distribution is already very close to normal. At infinity degrees of freedom, it equals the normal distribution exactly. This is why the CFA exam uses the threshold of n equals 30. Below 30, the t-distribution has noticeably fatter tails than the normal. Here is the decision tree the CFA exam expects you to follow. First question. Is the population normally distributed, or is n greater than or equal to 30? If neither is true, you cannot construct a reliable confidence interval with standard methods. If yes, second question. Is the population variance known? If sigma is known and the population is normal or n is large, use the z statistic. The confidence interval is x bar plus or minus z alpha over 2 times sigma over root n. If sigma is unknown, use the t statistic with n-1 degrees of freedom. The confidence interval is x bar plus or minus t alpha over 2 times s over root n. There is one special case, the exam tests. If the population is normally distributed and sigma is known, you use z regardless of sample size, even if n is small. If the population is normally distributed and sigma is unknown, you use t regardless of sample size. The deciding factor between z and t is whether sigma is known, not the sample size. Sample size only matters for determining whether the CLT allows you to assume normality. Let me work this with a t-distribution example. A sample of 16 hedge funds has a mean return of 12% with a sample standard deviation of 8%. The population is normally distributed. Population variance is unknown. Construct a 90% confidence interval. Step 1. Since population variance is unknown, we use the t-distribution. Degrees of freedom equal n-1 equals 16 minus 1 equals 15. Step 2. For a 90% confidence interval with 15 degrees of freedom, the t-value is 1.753. You would find this from the t-table at alpha over 2 equals 0.05 with 15 degrees of freedom. Step 3. Standard error equals s over root n equals 8 divided by the square root of 16. Square root of 16 is 4. 8 divided by 4 equals 2%. Step 4. Margin of error equals 1.75. 3 times 2 equals 3.51%. Step 5. The interval is 12 minus 3.51 to 12 plus 3.51. 8.49% to 15.51%. Compare this to what z would give. The z value for 90% is 1.645. Margin of error with z would be 1.645 times 2 equals 3.29%. The t interval is wider, 8.49 to 15.51 versus 8.71 to 15.29. The extra width accounts for the additional uncertainty from not knowing sigma. Part 6. Properties of an estimator. What makes a good estimator and how to judge quality. The CFA curriculum identifies 3 desirable properties of an estimator. First, unbiasedness. An estimator is unbiased if its expected value equals the true population parameter. Think of it as shooting arrows at a target. An unbiased estimator hits the bullseye on average. Individual shots may miss left or right, but the average of all shots hits the center. The sample mean is an unbiased estimator of the population mean. If you took every possible sample and averaged all the sample means, you would get exactly the population mean. Second, efficiency. An efficient estimator has the smallest variance among all unbiased estimators. Back to the arrow analogy. Two archers might both be unbiased, both hitting the bullseye on average. But the more efficient archer has tighter groupings. Her arrows cluster closer to the center, even though both archers center on the bullseye. Third, consistency. An estimator is consistent if it gets closer to the true parameter as the sample size increases. As n goes to infinity, a consistent estimator converges to the population parameter. The sample mean is consistent because its standard error, sigma over root n, goes to 0 as n increases. The exam often tests whether you can distinguish these three properties. Unbiasedness is about the center. Efficiency is about the spread. Consistency is about what happens as n grows. Part 7. Biases that destroy your sample. 5 types of bias the CFA exam expects you to identify and avoid. Data mining bias, also called data snooping bias, occurs when you test so many relationships on the same data set that some appear significant purely by chance. Imagine testing 500 different trading strategies on 10 years of stock data. At a 5% significance level, you expect about 25 strategies to appear significant even if none of them actually work. They pass the statistical test by luck, not because they predict future returns. The CFA exam often presents scenarios where a researcher reports an amazing result. The question is whether that result came from testing one hypothesis or from testing hundreds and cherry-picking the best one. The antidote to data snooping is out-of-sample testing. If a strategy works on the data you discovered it in, and on completely new data that was not used in the discovery, then the strategy is more likely to be genuine. The exam calls the original data the in-sample data and the verification data the out-of-sample data. Sample selection bias occurs when your sample systematically excludes part of the population. The most important type on the CFA exam is survivorship bias. Survivorship bias happens when you only study entities that survive to the present and ignore those that failed. Classic example. You study the returns of all mutual funds that exist today. Your database shows an average annual return of 9% over 10 years. But many funds that performed poorly were shut down during that period. Those failed funds are not in your database. If you included the returns of the closed funds before they shut down, the average would drop to, say, 7%. By only looking at survivors, you overstated the average return by 2 full percentage points. Survivorship bias always overstates performance because the worst performers are removed from the sample. This is heavily tested. The CFA exam loves to present a study conclusion and ask what bias threatens its validity. If the study only uses currently existing entities, the answer is almost always survivorship bias. Look-ahead bias occurs when you use information that was not available at the time of the decision. For example, testing a trading strategy that buys stocks with low price-to-earnings ratios. On December 31st of each year, you calculate the PE ratio and decide which stocks to buy. But annual earnings are not published until February or March of the following year. If your backtest uses December earnings to make a December trading decision, you're using information that did not exist yet. The strategy looks profitable in the backtest because it has an unfair advantage. It can see the future. In live trading, that advantage disappears because you would have to wait for the earnings release. The CFA exam tests this by describing a study that uses data from a later date to make decisions as of an earlier date. The fix is to use only information that would have been publicly available at the decision date. Time period bias occurs when the time period studied is too short or too long. Too short, and results may reflect a specific market condition that is not representative. Studying only the 2007 to 2009 period makes everything look terrible because that includes the financial crisis. Studying only 2020 to 2021 makes growth stocks look invincible. Too long, and the fundamental relationship may have changed during the period. A 50-year study of interest rate behavior includes periods with fundamentally different monetary policy regimes. The gold standard, Bretton Woods, free-floating currencies. Averaging across all these regimes masks the fact that relationships within each regime are very different. The CFA exam tests this by presenting studies where the time period chosen conveniently supports the researcher's conclusion. If the question says the study covers only a bull market or only a recession, think time period bias. Part 8. CFA Practice Questions. 5 exam-style questions with wrong answer analysis. Question 1. A sample of 49 observations has a mean of 15% and a population standard deviation of 7%. What is the 95% confidence interval for the population mean? Take a moment to work this out before I reveal the answer. The answer is A, 13.04% to 16.96%. Standard error equals 7% divided by the square root of 49, which is 7. 7 divided by 7 equals 1%. Since sigma is known, we use z. Z for 95% confidence is 1.96. Margin of error is 1.96 times 1% equals 1.96%. 15 minus 1.96 is 13.04. 15 plus 1.96 is 16.96. If you chose B, 13.4 to 16.6, you used Z equals 1.645. That is the 90% reliability factor, not 95%. This is a common mistake. 1.645 is for 90% confidence. 1.96 is for 95%. 2.575 is for 99%. If you chose C, 14 to 16, you use Z equals 1, which gives a 68% confidence interval, not 95%. Question 2. An analyst takes a sample of 25 stocks from a normally distributed population. The sample mean return is 9% with a sample standard deviation of 5%. Population variance is unknown. Which distribution should the analyst use to construct a confidence interval? Think about this. The answer is C, t-distribution with 24 degrees of freedom. Population variance is unknown, so we use t. Degrees of freedom equal n-1, which is 25 minus 1 equals 24. If you chose A, Z distribution, you forgot that Z requires known population variance. The question specifically says population variance is unknown. Even though the population is normally distributed, unknown sigma means t. If you chose B, t-distribution with 25 degrees of freedom, you forgot to subtract 1. Degrees of freedom for a single sample confidence interval is always n-1. This is an easy point to lose on the exam. Always subtract 1. The exam loves this distinction. Normal population plus known sigma equals z. Normal population plus unknown sigma equals t with n-1 degrees of freedom. Non-normal population plus large n equals either z or t depending on whether sigma is known. Question 3. A researcher finds that a particular trading strategy produces significant positive returns when backtested on 15 years of data. However, the researcher tested 200 different strategies on the same dataset before finding this one. Which bias most likely threatens the validity of this result? Think about this carefully. The answer is B, data mining bias. Testing 200 strategies on the same dataset is textbook data snooping. At a 5% significance level, you would expect about 10 strategies to appear significant by pure chance even if none of them actually work. Finding one significant result after 200 trials is exactly what randomness would produce. If you chose A, survivorship bias, that would require the study to exclude failed entities. The question says nothing about excluding funds or strategies that failed. The issue is multiple testing, not missing data. If you chose C, look-ahead bias, that would require using future information in a past decision. Question says the backtest uses 15 years of historical data, but does not mention using data that was not available at the decision time. The key phrase that signals data mining bias is tested 200 different strategies on the same dataset. Whenever you see multiple testing on the same data with cherry-picked results, data mining bias is the answer. Question 4. A study of mutual fund performance over the past 20 years finds an average annual return of 11%. The study includes only funds that are currently in operation as of the study date. The most likely effect of this bias is that the reported average return is. What do you think? The answer is A, too high or upward biased. This is survivorship bias in action. By including only funds currently in operation, the study excludes all funds that closed during the 20-year period. Funds closed primarily because they performed badly. Investors withdrew money, assets under management dropped below a viable level, and the fund manager shut it down. When you exclude the worst performers, you pull the average upward. The reported 11% includes only winners and middling performers. If you included the failed funds with their typically negative or very low returns, the average would be lower, perhaps 8 or 9%. If you chose B, downward biased, you would need a mechanism that excludes the best performers. There is no such mechanism here. If you chose C, unbiased, you would need all funds, including closed ones. The study explicitly excludes them. Remember this rule for the exam. Survivorship bias always biases performance upward because you are removing the losers from the sample. Question 5. The central limit theorem states that as sample size increases, the sampling distribution of the sample mean will. Choose carefully. The answer is B, approach a normal distribution. The central limit theorem says the sampling distribution of the sample mean approaches a normal distribution as n increases, regardless of the shape of the underlying population. If you chose A, approach the distribution of the population, you have it backwards. The sampling distribution becomes normal even if the population is skewed, uniform, or bimodal. It does not become more like the population, it becomes more like the normal distribution. The population distribution is irrelevant once n is large enough. If you chose C, have a variance equal to the population variance, that is also wrong. The variance of the sampling distribution is sigma squared divided by n, not sigma squared. As n increases, the variance of the sampling distribution actually decreases. It equals the population variance divided by n. This is why the standard error formula has root n in the denominator. The CLT tells you about the shape of the sampling distribution, specifically that it becomes normal. It says nothing about the distribution matching the population. Let me connect all these biases back to real-world practice. In 2003, 2 researchers at Duke University studied all published trading strategies in academic finance journals. They found that strategies backtested on the same popular databases showed significant return premiums. But when they adjusted for the number of strategies tested across all papers using those databases, most premiums disappeared. The entire academic factor zoo, hundreds of factors claimed to predict stock returns, was largely a product of data mining across shared datasets. Survivorship bias has been estimated to inflate historical mutual fund returns by about 1 to 2 percentage points per year. The Morningstar database, widely used in research, now includes dead funds specifically to combat this bias. Look-ahead bias was famously exploited by traders who used preliminary GDP estimates in their models, not realizing those estimates get revised months later. The backtested strategy used the revised final numbers, but in live trading, only the preliminary numbers were available. This strategy failed live. Here is your complete sampling and estimation cheat sheet. Save this, screenshot it, review it before the exam. Every formula, every decision rule, every bias definition in one place. Pause here if you need time to study each item. Before we close, let me give you the exam pattern recognition you need. When the question says population variance is known, you use Z. When it says unknown or gives you a sample standard deviation, you use T with n-1 degrees of freedom. This is the single most common testing point in this topic. When a study only includes currently existing entities, think survivorship bias, direction is upward. When a study tested many strategies on the same data, think data mining bias. When a study uses data not available at the decision time, think look-ahead bias. When a study period conveniently matches a specific market condition, think time period bias. For confidence intervals, memorize 3 Z values: 1.645 for 90%, 1.96 for 95%, 2.575 for 99%. And remember, higher confidence means a wider interval. You are more confident precisely because you cast a wider net. Master these patterns and this topic becomes easy points on the exam. That is sampling and estimation for the CFA Level 1 exam. You now understand how to draw valid samples, how the central limit theorem makes inference possible, how to build and interpret confidence intervals, when to use Z versus T, and how to identify every bias that can destroy a study's conclusions. In the next lesson, we tackle hypothesis testing. You will learn how to test whether a claim about a population is true or false using the same statistical framework you just mastered. If this lesson helped you, subscribe and turn on notifications so you do not miss the next one. CFA Exam Mastery. Let us pass this exam